we go. All right, so remember when we did this before, we already got our solutions because we looked for them, right? We found the, hold on. We already found the equilibrium points, right? We were at 0, 0, 0, 3, 2, 0, and then 1 and 1. Okay. And so here we're going to go ahead and do this, and we'll just do this one in the computer. And for this one, we'll just go ahead and say that it's positive, just so we can look at this. So let's open up the computer and look at this one. So let's look at something a little bit more fancy. I need to open up the program. I had the notes open, but I didn't open the program. All right, so I am using this. You can use whatever you want. I'm just using this. It's free. So let's go ahead and type this in. So we have 2x. Oh, remember this one you have to type in. Oops. 2, 3, 1 minus x divided by 2. And then for this one, we have 3 star y star 1 minus y divided by 3 minus 2 star x star y. And here, let's go ahead and do, let's just do the first quadrant. Yeah, let's go ahead and draw in some sample lines. All right, so here we can kind of see how it is. Well, let's kind of draw it by hand now. We'll leave that off to the side. So here, what do we have? Well, we have here, if I was going to draw this a little bit by hand, I have our 0, 0. I have our 0, 3, so 1, 2, 1, 2, 3. Let's make this a little bit more even. We'll have 1, 2, have a point here, and we have a point here. These are equilibrium points. So what's happening? What's happening? Let's look at this thing again. So here it comes in and goes this way, so it kind of scoops into our equilibrium point. And so here, as I draw this, it's kind of this weird, I think we can draw it a little bit better. So stuff kind of comes, so it comes this way, or it swoops this way, or it swoops this way. And so here's a much more intricate directional field. And notice here, once again, these are seem to want to go to the equilibrium points. This isn't always true, right? This things around this equilibrium point. If I'm not exactly on these little happy lines, they kind of just shoo away from it. Like here, it kind of go away. And so here's another notion of our vector field. So, all right, so let's, I think I wrote this twice for some silly reason. let me, oh no, here we have the undamped and damped. So here, by setting the first derivative of function to a new function, logically convert a second order ODE into a system of ODEs. And this can be repeated for a higher order. And let me kind of explain what we're doing here. So here, let's go back to our undamped harmonic oscillator. So here we have F equals MA, which equals M d n d dx. Let's go ahead and put this in t. I'll leave it in t for now. T squared, and that's equal to, which implies that m dy squared over dt is equal to minus ky. And then we got it back to this where we have this d dt squared plus k over my equal to 0. So here we have this, and this is second order, right? This right here is second order. Well, I can introduce something. I can say dy or dv or dt is equal to v, right? The change of position is equal to velocity. And doing that, I can write this as d dt d dy dt equals k, oops, not equals, plus ky over m equals to 0. Rewrite this, I can change this into dv dt equals, and I'll go ahead and move it over, minus ky. And then what do I have here? dy dt is equal to v.
Sorry, real quick. When you have the ddt of dy dt plus ky over
m,
okay, cool. Just wanted to make sure.
there you go. This is an m. Sorry. Yeah, so this is m. So here I just divided out m. So here, what do I have? Here I have a second order that I've converted into a first order system, right? Because this only has one derivative and this only has one derivative. So here I've converted the second order into a first order system. We can do the exact same thing here. We just won't go through all the steps as much because here I'll have d squared y dt squared plus, in this case, our damping coefficient. B or C. I think we were using C, so let me use C. Over m dy dt plus k over m y equals to 0. So here we have our this. So this is second order, right? So second order. But here we can introduce the y dt equal to b. Once I do that, I can replace everywhere I see dy dt with a b. So this would be d dv dt plus c over m dy, or dy dt. Well, dy dt is just b plus k over m y is equal to 0. Well, in this case, what happens? We get dv dt. So this implies dv dt equals to minus c over mv minus k over my. And here we have a system again. And so this is a first order system where here we have y in terms of dy dt's in terms of v and y, and dv dt's in terms of v and y. And so here we converted a second order system into a second order equation into a first order system. And this is useful. And you can do this to simplify things and to clear out things. And so this is quite nice. It's just something we'll be using from time to time. So let's go ahead and export this and go to the next one. All right, Photoshop, I want to export this. Thank you. Yeah, that's fine. All right. All right, so let's talk about let's actually get into solving some things. Any questions on any of this? I don't see them. Okay. All right. All right, so checking solutions of ODE. So here, we're going to have solutions that are going to look vaguely like this, right? And I want to check if this is a solution. So let's just start. Let's see how I can say this correctly. Let's just see if certain things are solutions. All right, so how do we do this? Well, this is dt of x, right? dy dt, and this is equal to minus x plus y minus 3x minus 5y. So here I've taken it out of vector notation, just put it back into a system notation. Then what am I going to do? I'm just going to plug in what x and y is. This is x, this is y. So that implies the derivative of e to the minus 4t minus 3e to the minus 2t over dt. This derivative is equal to minus x, which would be e to the minus 4t minus 3 e to the minus 2t. So the minus carries in, so this becomes positive. So minus, and then carry that in becomes positive. Then plus the y, which is right here. So this is minus 3 e to the minus 4t plus 3 e to the minus 2t. Okay, so here I plugged in, this is minus x right here. This is the positive y, right? Minus x positive y. If I took this derivative, I'll get minus 4 e to the minus 4t, right? Minus 3, or no, minus 3, but the negative 2 comes out, so this would be plus 6, right? E to the minus 2t. And what we have on this side, if I get minus 3 minus 1 plus minus 3 is minus 4 e to the minus 4t plus 6 e to the minus 2t. So this one checks out, but then we also have to do this one, right? So here we're going to do this with respect to y. So dt of y, which is minus 3e to the minus 4t plus 3e to the minus 2t equals minus 3 times x, which would be e to the minus 4t plus 9 e to the minus 2t. And then here we have minus 5y, so that would be minus 15. So no, minus, and so 5, that would be minus becomes plus 15. Sorry, just to make sure I get everything in the right order. Minus 4t, and this becomes minus 15 e to the minus 2t. All right, so we'll simplify this. So if I take this derivative here, I'll get 12 e to the minus 4t minus 6 e to the minus 2t. Here, if I collect the 4t's, here I have minus 3 plus 15, so that gives me 12 e to the minus 4t. And then here I have a positive 9 and a minus 15, so that gives me minus 6 e to the minus 2t. Does that check out? Yeah. Okay, so that makes sense. What goes where, what goes what, and I don't know. Sometimes it's like, well, what's the solution? It's like, I don't know. It's like, but if I don't do this once with you guys, it's like when we get to these fancy solutions, because our solutions are going to very much look like this, right? They very much will look like this. I want you to be able to check them, and what you do is you just plug in everywhere you see an X, you just plug this in, and everywhere else and check them. So there's no reason, since all this we take home, to not check them, right? All right. So let's start solving things. So here we have a completely decoupled system. So a completely decoupled system of ODEs, where each ODE only depends on one dependent variable. So these can be solved and included using the old methods we've learned before, right? So this system is completely decoupled. Why? Because this only depends on X. This only depends on Y. So how do we solve this? Well, we'll just call this equation 1 and this equation 2. Let's just solve equation 1. So equation 1 is, so this means that, hold on, let's be very clear what we're doing here. So here we have, so here if we just solve it, we know this is equal to k1 e to the minus 2t. Equation 2 is y is equal to k2 e to the minus t. And so here we have this, our solution. If our y vector of t is equal to, if we want to write it in vector notation, this is x and y, which is also equal to k1 e to the minus 2t and k2 e to the minus t. All right. And let me make a little notice here, a little notice for advance. Notice that k1 and k2 are different. So don't combine right now. So don't combine these. Usually when you have two constants, you multiply or add them together, you'll think, oh, I can just combine these. Don't do that right now because it might lead to problems. So don't combine. So when you have your, when you produce this, every time you're going to get a different constant, and you don't want to combine them right now. Okay. All right, so that's the end of this page. Let's go ahead and exit. Hit the save button. All right. What's after that? Oh yeah, this is e to the minus 2. Yeah, you guys got it. Okay. Kind of just fell off the page. So let's look at a partially decoupled system. So here we have partially decoupled. So partially decoupled only depends that some only depend on one dependent variable, and the others can be solved using older methods than plugging one into another. So what do I mean by that? Let's just actually look at this one. So let's call this equation 1 and this equation 2. So we're going to solve this one. All right, so let's solve equation 2. So we'll start with equation 2. This means that y is equal to some k2. It's just because it's equation 2, I'm going to write k2, right? E to the minus 4t, right? We know how to solve this. In fact, at this point, you should be able to look at this and say, hi, that's exponential decay, and just write it out. All right, so I get this. So what do I do with this? Well, I plug it in to 1. And so I just plug this into 1. And so here I'm going to say dx dt is equal to 2x plus 3k2 e to the minus 4t. All right, so what am I going to do from here? Let's go ahead and just move some stuff around. So here I'll have x prime minus 2x equals 3k2 e to the minus 4t. What does this look like? This looks like a linear equation with constant coefficients, right? Non-homogeneous linear equation with constant coefficients. So if you remember what to do, we use an integrating factor. So here I'm going to use some u of t equals e to the minus 2 dt, which is equal to e to the minus 2 et. And so x of t equals 1 over e to the minus 2t integral of 3k2 e to the times e, so minus 4t times this, which would be e to the minus 2t plus c. Remember, we multiply across everything. All right, so that gives us x of t as we solve for this. These two come together, become minus 6t. I'll skip less steps. Let me skip less steps. So this is e to the 2t. Just leave it like that. Here, if I simplify this, this is the integral between 3k2 e to the minus 6. Sorry, that should be a 6. Hello. Thank you. 6t plus, and let's, instead of just saying this is c, we're going to just call this k1. Let's just call this k1. In fact, let me just, for consistency, instead of a c here, let's just put k1 to make sure it's the constant for the unknown constant for the x variable. All right, now if we do this, what do we get here? Well, if I take the integral here, let's get the negative 6 will pop out, so I'll have minus 2 k2, or minus a half k2 e, and then here if I multiply this times this, so this would be minus k2 over 2 e to the minus 4t. So when I take this integral, I get negative k2 over that e to the negative 6t, but multiplied by e to the 2t, I'm going to get e to the minus 4t plus some k1 e to the 2t. All right, so here we have our solution. So what's our solution in this case? Our y of t, so our y vector of t, remember again, this is xy. I'm going to try to get you a little bit more used to this notation. So here, it's minus 2k e to the minus 4t plus some k1 e to the 2t all over k2 e to the minus 4t. And so here's our solution. And notice how this solution is not too terribly far from something that looks like this, right? And so we're getting closer to, this is actually a real case. This isn't me just throwing in random numbers. This is what our solutions are going to look like. So here we have a partially decoupled system. How do we solve it? Well, we solved it by solving the one that's the decoupled part, right? The part that's only one. Here we can just solve this using method. Here we have a linear with constant coefficients. We use this technique right here of integrating factors, and we just integrate it across, and we get a solution. And here we got our solution, and then we just put it together. Okay. So there, you've solved your first kind of non-trivial system. All right. Any questions on this one? Hi. All right. So let's go ahead and export this as a PNG. Ta-da. All right. Let's get moving. So I need to open up more notes. My computer only really handles 3 at a time safely. Because I'm also running Zoom, I'm doing video processing, blah, 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 right? What am I looking for? Type notes, chapter 4. Sorry, guys. Open with Photoshop. We want pages 7 through 9. All right, let's open those up. Whoop. All right, so let's go back into it. So let's talk about, all right, so let's get some nomenclature. So a first order system. So what we mean by first order system is here, if we have a system, if we're given a system, the function that can be given, it can have variables of this, see, I can say this correctly. It can be both, so x and y are variables. So each differential part can be a function of x and y and x and y. So this is the way we're going to kind of leave it for now. because we want our systems to be linear, right? And so we always try to keep it to like a first order. So this is the first order system. So that means this is the system here is order 1, right? And then here I can have everything else here. So the derivative has to be clean, right? So our derivative has to be clean. If there's a 6 or 7 over here, we can just divide it out, right? Of course. And for a larger case scenario, let's just let me just rewrite that. So if you're at d of v dx dt equals some function of x, y, and z, and so forth, right? And so here, if it was a third order system, if I had 3 things in my system, it would still be that. It's just still first order system, just with my system size would be 3, right? So this is a 2 by 2 system. This is a 3 by 3 system. If we simplify that even more to constant coefficients, we end up with this, right? So if it's a function with constant coefficients, and we want it to be a linear, first order linear system, so this is what it means, right? It means I just have some ax plus by plus cx plus dy. And so the reason that this becomes super nice is that now I can write, so I'm writing this in vector form, I can write this in matrix form, right? And I can write the whole system into this form. And that's kind of the goal, right? Because here I can have a derivative of a vector equals a matrix times a vector. And since this is first order and linear, we have the linearity principle. So let's let this, so if y of t is a solution to our differential system, right? And we have some constant, that's also a solution to the system. And if so y1 of t is a solution and y of t is a solution. So if I have 2 different solutions, then we can add them up and get solutions. Therefore, we can get this, and this is known as our general solution. And so guess what we're going to try to look for? We're going to try to look for 2 linearly dependent solutions, right? This one's independent of this one. The book goes into the Wronskian, is like, here we can show this is linearly independent, blah, 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 blah. All of that's really nice, but you guys are engineers, you just don't care, right? So let's just get to the point, right? You just want 2 linearly independent solutions, and then this forms a general solution. And as long as these are linearly independent, the span will encompass all of R2. So basically, there's a theorem out in linear algebra. If I have 2 linearly independent vectors, if I have n linearly independent vectors in the space Rn, the span of those vectors is Rn, right? So here, if we have 2 linearly independent vectors for my R2, so R2 is the plane, right? R2 is the real plane. R3 is the complex, or the 3D plane, right? R3 is a 3D plane. R4 is 4th dimensional. Eventually, further in math, you get into n-dimensional planes, and then you get into really funny spaces, right? Spaces that, like Hausdorff spaces, which I doubt you guys will get to, right? So here, and then, so once we have this, we can use our initial conditions to figure out what K1 and K2 are. And then we can find our particular solution. And that's kind of the goal. So the goal of this chapter is just to find two of these solutions, 2 such solutions. We find these 2, we do this. Is that a derivative times a vector? Yes. Oh, hold on. Shouldn't K2 be in, hold on. Did I mess up something on the last one? It says, shouldn't K2 be in the X?
In the solution on the last page, where it was vector x, y equals all that stuff right in the beginning, you had k over 2, but it's supposed to be k2 over 2.
Oh, thank you. Thank you. Yeah, it should be K2 over 2. Yes, thank you. That's it. Thank you. All right. Okay, so that's our goal. So let's get to it. Let's do page 8. There we go. Boop. Zoom on in. All right, so solve the following. So solve the following system and give the general solution. Can't use the previous problem, right? So we did this, right? So here is the problem we just did, literally on the other page. This one. Yeah, right. Because here I haven't. Because let me show you. It's the same. So here I have dx dt equals dy dt. So if I convert that over, I get that. Here I'll get. Remember, x vector is x times y, so it'll be 2 times x plus 3 times y, so it'll be 2x plus 3y. This will be 0 times x minus 4 times y. This looks super familiar? It should, right? It should. And so, we want to find two linearly independent solutions. Well, see how I can write this to not get people confused. All right. So here, and what did we get? What did we get for solutions? We got x of, oops, we got x of t is equal to, see if I can be very careful when I write this. We'll have k2 over 2 e to the minus 4t. Gee, I'll have to go back to my answer. Hold on. There we go. E to the minus 4t plus k1 e to the 2t, and then we have y of t equal to k2 e to the minus 4t. That's what we got, right?
And then just plus before that k1 and the second part of x.
Oh, yes, you're right. Thank you. All right, so I want to write this, but I want to write this in y1 in terms of y2. So here, I'm going to go ahead and put this back into vector form. So here I'm going to have b of t.
I think the k2 over 2 might have been negative as well, not positive.
You're right. I have the negatives in the wrong spot. Negative was here, positive was here. Okay. So let's do this. So here, I'm going to write, so here I have a bunch, I have basically the same thing, right? So here I have minus a half and a 1, k2 e to the minus 4t plus, here I have a 1 and a 0, k1 e to the 2. Does everyone see how I produced this from this? I want to make sure this is clear to you guys. So here, I'm writing this in vector form, right? So when I add up the top vector, I should get negative a half k2 e to the minus 4t plus 1 k1 e to the 2t. On the bottom half of the vector, I'll have 1 k2 e to the minus 4t and 0, because I have no e to the minus 2t here at all, right? And so here, I've shown this. Now, the real easy part is this linearly independent? Yes, this vector is linearly independent from that vector, right? This vector is not a multiple of that vector. And so let's learn how to plug some stuff in. All right, so let's just do the following. Let's just plug in a whole bunch of initial conditions and get you past the point where you can safely put in initial conditions. So what am I solving for here? I'm solving for K1 and K2, right? Or in this case, K2 and K1. So here, if I have this, so if I have 2 comma 0 are my initial conditions, so y of 0, and here y of 0, Why not is another way of saying why plug in 0. Okay, for us, that's what we're going to be using that as. So the numbers in the parentheses are what in front of you. Yeah, so the number in parentheses, so here I've turned this from a system into a vector. So this is the vector half 1, and then the vector 0, 1. I use parentheses when I teach. Notice that this is functionally equivalent to this in terms of notation, right? So these are equal for our notation. I just use the parenthesis notation for writing these notes just because it gets cleaner for long periods of writing by hand. All right, so let's do this. So here, well, if I plug in t equal to 0, right, what happens to this? What happens to this? Well, this part becomes 1, right? And this part becomes 1. And so if I plug in t equal to 0, here I have minus a half 1 of k1 plus, or k2, sorry, and then 1, 0, k1. What do I know here? Well, here, do we need to put this into a system of equation and solve it and put it in RE or reduced row echelon form? No, right? Here I know the bottom part better be 0. That means k2 has to be 0 because there is no k1, right? That means k2 is 0. k2 is 0, right? That quickly is, because here if I wrote this out real quick, this would be 2 equals minus a half k2 plus 1 k1, 0 equals 1 k2 plus 0 k1. That's what this means, right? This and this are the same. So k2 is 0. That means k1 is 2, right? That means k1 is 2. Oops, k1 is equal to 2. And so we have our solution here. And so our solution in this case, so y of t is just equal to 2e to the 2t 1, 0. So that is our solution. Here, let's do another one. Let's do another one real quick. So here I have minus 1 and 2, and we have, so here I'll have minus 1 and 2. We want to solve the following is minus a half and 1, k2 plus 1, oops, 1 and 0, k1. Well, what does this end up equaling? So how would I do this one? Well, here I'm forcing what k2 should be, right? This will force what k2 is. k2 better equal to 2 because I can get nothing from here. So k2 equals to 2. But if k2 equals to 2, this is a half, and so that means k1, oops, is equal to 0. And so here we have our function y of t is equal to, hold on, my brain just keeled over and died. Minus a half 1 times 2 e to the minus 4t. And if you want, you can stuff the 2 into here. That's perfectly fine as well. So another way of writing this would be y vector, I'll put my little vector hat on, of t is equal to minus 1, 2 e to the minus 4t. And this actually makes a little bit more sense to write it this way. Okay. All right, so let's do something that's a little less trivial.
Can I ask a quick question? I'm
Yes.
sorry. How you wrote the y vector for the final answer at the top and at the bottom, is there any reason for putting the vector or the matrix before or after the equation?
No.
Okay.
So technically, this is a scalar according to mathematical world, and this is a vector or a matrix, right? So a scalar you can write on either side of the matrix.
Mm-hmm.
for whatever reason, I don't know, I just started doing it. It doesn't matter. When we
Okay.
start solving these by hand, I probably will have it the other way. Hold on, let me just make sure I'm not lying. Let me look forward to my notes. No, I do it the other way from then on. I think it's because the reason I did it this way is I wanted to show clearly that these, I show you, the only reason it's here first is because when I was teaching it, I was like, hi, this and this, what's up front is your scalar, and then everything else is attached to it. And this is your coefficients, that's what's attached to it.
Okay. Gotcha. Thank you.
Oh, it's a good question. It's a good question. So here, let's do this one last time. So 1/2 and 1. I figure by the fourth time I do this, you guys are going to be experts at this. I'll only do it 3 times though. All right, so what do we have here? So here, I have to solve the K2 first. So K2 equals what? K2 better equal -3, right? K2 equals -3. What does K1 equal? I'll have you guys give me the answer. What's K1 equal? If K2 is -3. A half, yeah, half's correct. So here we have a half. All right, so because here if I plug in -3, I get -3 halves plus, so negative, so this becomes negative, so this becomes positive, 3 halves plus a half, that gives that. So here's our answer. And so here, this is going to be the one that looks a little bit more interesting. Actually, we got room. Let's write it down below. That way I'm not squishing it in. We'll have y of t. And this time, I'll go ahead and write the minus 4t, the way you'll probably see it. And so here is -3. I'm going to just stuff that in to my vector. And so here I'll have -3 halves over -3. And then here I'll have plus e to the 2t, sorry. The 2t, this is a half, so okay. You're right, that should be positive. If I plug in the negative, it becomes positive. How do you get the k values? So how do we get the k values one more time? Okay, we did 3 times. Let's do it. Let me explain. Here, I always, for at least in this case, right? At least for this case, I'm always just going to look at K1 because, or K2 because K1 is 0 on the bottom. This will force what K2 is. Once I know what K2 is, I can just reverse substitute back into this. If you get lost, go ahead and expand this out into a system of equation. 2 equals 1/2 K2 plus 1 K1, 0 equals 1 K2 plus 0 K1, and then solve this using RREF. We'll solve more of these, trust me, we'll solve more of these. Okay. All right. Let's do the next page. All right. So let's solve something. All right, so let's start solving things. So here, so given this, we're going to solve in general. We want to solve this and give the general solution in vector form. Then solve the IVP when we have 2 and 3. All right, so here I'm gonna give you a second order. I'm gonna say, give it to me as a system and solve it. So the first thing you need to do is swap it over. So here we're going to introduce dy dt is equal to v. That's always what you do to do this. Then we plug that into here. So dv dt plus y equal to 0, which implies dv dt equals to minus y. So here we have our system. All right. I think for a second, I may not have given you all the ways. Okay, so let's do this. I'm trying to remember why I put this here. Right, 20 pages of notes. You're like, okay, what were you thinking when you did this problem? Let's do this. So here, let's go ahead and write this system. So here we have it as dv, and dy is y and b, right? Is equal to this system here will be 1, 0, 0, minus 1 of, nope, I have that backwards. Don't mind my dyslexia. It should be 0, 1, minus 1, 0 of y, b. Okay, and so, oops, this is d, dt. That's d. So hard derivative here. So now we have written this into the form we wanted. Equals 0, 1, negative 1, 0, y, and b. All right. So let's solve this before we know how to solve it. And I'll teach you how to solve it. I want you to be able to think through something. Do we know what the solution is to this? Do we know what the solution is to this? For a second order system. For a second order equation. Do we know what the solution is here? Yes, it's K1 equals, now what is y? What is y? Do we know?
E to the ix.
E to the ix. You're correct. E to the ix. Once we have e to the ix, what did we really use here? We used the Euler's formula, and then we proved that. That's fine. That's fine. I'm okay. Let's start there. Let's start where you know. Let's start where you're at. We have e to the ix. We're going to use Euler formula to convert that into cosine x plus I sine x, right? And then we want two independent solutions, right? And so here we have plus or minus e to the ix. But notice here we just took the real part and the imaginary part, so we got y was equal to some c1 cosine of x plus some c2 sine of x, right? That's what we got. Is everyone okay that this is the solution? Something cosine x, something sine x. But unfortunately here we're working with t, so the ix was not actually a correct answer because our independent variable here is what? T. So let's keep everything in the same independent variable. Okay. So this is our solution. Then what's v? If I know this is y, what's v? Y equal to 0 is a solution. Well, that is a solution. It is the trivial solution, but it is a solution. You're not wrong. What's v in this case? If I have y is equal to c1 cosine of x plus c2 sine of x, that's what our solution is for our second order simple equation. Yeah, derivative of y. Yeah, it's just the derivative of that. That is literally how we define v. So we just take its derivative. So this becomes minus c1 cosine of t, or not cosine, sine of t plus c2 cosine of t. All right, now can I write this in terms of k and stuff? Yeah, so this, since from what we know from up here, so this and this both imply to give us what? Y of t is equal to some constant. I'm going to go back to k's just so we have it consistent, right? So c1 will turn into k1. We'll just leave it to c1, doesn't matter. It really doesn't matter. So we'll just leave it to c1. c1 times this vector, cosine t minus sine t, right? Plus some c2 sine of t cosine t. Okay. All right. So this system is not decoupled at all, right? There's no decoupling. This one involves the other one. This one involves the other one. But from what we knew, we could produce an answer, and we did produce this answer right here. Y of t equals this. Now, what do I need to do? I just need to find out my initial condition. So y of 0 is equal to 2 comma 3. Or not 2 comma 3, 2 of vector 2, the vector 2, 3. Vector 2, 3. Which is equal to, well, if t is 0, what does this end up being? C1, what's this vector? 1, 0, right? What's this vector? 0, 1. So it's C1? Well, it's 2. Oops, I forgot my C2, didn't I? Oops, let's go back. So sine of 0 is 0, cosine of 0 is 1. So what do I get here? I get C1 equals to 2, C2 equals to 3. So my final answer here is 2 times cosine of t minus sine t plus 3 sine of t cosine of t. Yep. All right. All right. So we want to find two independently solutions. So we're going to first try to look for something we call straight line solutions. We want two linearly independent solutions, therefore we're going to turn to eigenvalues and eigenvectors. And so all the stuff we learned about eigenvalues and all the stuff we learned about eigenvectors are going to really matter, right? And so we're going to show that this guess provides solution. And let me show you how this guess provides a solution. So so here we're going to have this. So we're going to start with this. dy dt is equal to a lambda or a vector. So, and remember what this is. This is nothing more than this, right? I'm going to take this system, I'm going to rewrite it like this. Then I'm going to use that. So I'm going to start here, and I'm going to guess. I'm going to guess some. I'm going to use the guess that y sub 1 or y sub some solution, right? I guess I'll put a little g. Y guess is going to be some e to the lambda t times this, right? And I'm going to make it, and here I'm choosing lambda, and lambda by definition is going to be an eigenvalue. An eigenvalue for a, right? An eigenvalue for a, and v lambda will be the corresponding eigenvector. So this will be its eigenvector. So let's see what happens when I plug that in, right? This should not be equal. So we're going to guess this should be multiply. Sorry. So let's guess this solution and plug it in. So if I plug this in over here, I get e Let me make that not look like a v, more like a y. So here, e to the lambda t v, oops, hello. Can we not do that, please? Thank you. dt. So here I'm plugging it in on this side. V lambda. And then over here, we're going to have a e to lambda t v lambda. All right. So all I'm doing is just saying, I'm going to guess that this is the solution, right? And plug it into my system. Well, here, if I take its derivative, this is just going to be some constants. And here I have lambda t. So the derivative of here is lambda e to the lambda t v lambda, right? And notice, let me just do something. And this is equal e to the lambda t a b lambda. But remember what it means to be an eigenvector. If this is truly an eigenvector, multiplying a by it is the exact same thing as multiplying lambda by it, right? That's what it means to be an eigenvector. Because if it was an eigenvector, we wanted to find something that's we wanted some constant, right, times a vector equal to a times the vector, right? That's what it was. That's what we solved for. And that constant, that thing was lambda, and we call this the vector lambda. So that's what it means to be an eigenvalue. So there I can imply that in this. Does this equal this? Yes. And so this is the solution, right? These are our solutions. So guess how we're going to start finding solutions? So that's for one eigenvalue, right? And so if the eigenvalues are linearly, so if lambda 1 does not equal lambda 2, right? And let's just for now say they're real, right? Then the guess of v1 of e to the lambda t vector and v2, and like v1 lambda 1 e to the lambda 2 t.
Those are V's or Y's, the vectors in the last line.
So this is a y, this is a v. This is a y, this is a v. I know it's terrible because I have to use the uppercase y. I guess I could use the lowercase y, but then the difference between this and this gets hairy, especially if I forget to do that. So if I always use uppercase y's to intercase the vector and the lowercase y's to intercase the variable, it's less troublesome. Does that make sense? So here I have one solution is the eigenvalue times e to the lambda t times one of the eigenvectors, and the other solution is e to lambda t times the other eigenvector. And since these are real and not equal to each other, these should be linearly independent, LID. So these are linearly independent, and therefore we can create our general solution, which will be e to the lambda 1 t v lambda 1 plus, oops, I forgot something. Hold on. K1 e to the lambda 1 t v lambda 1 plus K2 the lambda 2 t v lambda 2. Okay, so that produces our first solution. All right, we're going to end it here today. So we got 6 pages in, so that's good.